In the world of manufacturing, there are few things more frustrating than a part that fails. Today, we're going to talk about metal casting defects, those tiny flaws that can force you to scrap an entire production run. But what if I told you these failures aren't just random bits of bad luck? What if they're predictable, solvable, and yeah, even preventable? All right, let's get into it.
So take a look at this. This right here is a shrinkage cavity. Now, for a foundry, this isn't just a flawed part. It's lost time, it's wasted energy, and it's a real hit to the bottom line. This is the kind of thing that has you up at night questioning your entire process. Was the metal too hot? Did we prep the mold wrong? The questions just start piling up. And that brings us to the big question for today. Is a defect like that just a random failure, an accident? Or is it the logical, totally predictable result of the physics that are happening deep inside that mold? We're going to make the case that it's absolutely the latter and show you how just shifting your perspective can change everything.
Okay, so to really understand this new way of thinking, we first have to look at the old way. Let's dive into the traditional view of how you diagnose and fix these casting defects. For decades, when a defect showed up, the go-to move for foundry managers was to pull out the handbook. And inside, they'd find a table that looks a lot like this one. So, you've got a porosity problem? Well, the book lists dozens of potential causes across all these different categories. Your gating design, the sand quality, the metal chemistry, your melting practice, you name it. The idea was you just work your way down the list, trying one fix at a time. Well, as you can imagine, this trial and error method turns quality control into a very, very expensive game of whack-a-mole. You might patch up one problem only to have another one pop up somewhere else because you're just treating symptoms. You're not getting to the root cause, the underlying disease. And here it is. This is the crucial pivot. What if porosity and carbides and shrinkage, what if they aren't dozens of separate problems? What if they're all just different symptoms of the exact same fundamental process going just a little bit sideways? Thinking about it that way, well, that changes the game completely. So, let's reframe this whole thing. A casting isn't just a shaped piece of metal. It's really the end result of a controlled physics experiment. It's a story written by the laws of thermodynamics. The absolute star of this story is a process called solidification. This is that magical moment where molten metal transforms into a solid, crystalline structure. But, it doesn't just happen instantly, like water freezing in an ice cube tray. No, it's a really complex, dynamic journey with a ton going on at the microscopic level.
Now, what's so cool is that we can actually break this whole journey down. The final quality of any casting is really decided by this constant dance between a few key forces. You've got how heat flows out of the casting, you've got the precise chemical recipe of the alloy, and then there's this fascinating physical battle of expansion versus contraction happening right inside the metal itself. Let's zoom in on that battle of volume, because this is where so many defects are born. You can think of it as a thermodynamic tug-of-war between two powerful opposing forces. See, on one side of the rope, you have shrinkage. As the iron starts to solidify into its main crystal structure, which is a phase called austenite, it actually shrinks and pulls away from itself, creating these tiny little voids. But on the other side, you have expansion. As the carbon in the iron separates out and forms graphite, it expands, pushing outward. And this expansion is what helps fill in the gaps left by the shrinking iron. So the health of the final casting really depends on which side wins this internal tug-of-war.
And this whole battle takes place in a region with a great name, the mushy zone. It's literally a semi-solid slush where these solid crystals, or dendrites, are growing inside the remaining liquid metal. Now, for the good guys, the graphite expansion, to win, liquid metal has to be able to flow through this mushy zone to feed the areas that are shrinking. The permeability, how easily liquid can flow through this zone, is everything. And this image just illustrates that perfectly. Look on the left. That's a scenario where the solidifying crystals form this dense, tangled wall. It chokes off the flow of liquid metal, basically starving the last parts to freeze and creating shrinkage defects. But now look at the right. The crystal structure is way more open, kind of like a highway, allowing that liquid to flow freely and make up for the shrinkage. It's the same metal, but a totally different outcome, and it was all decided by the structure of that mushy zone.
So you're probably asking, how on earth can we see this complex thermodynamic story as it's unfolding inside a red-hot mold? Well, the answer lies in a simple, really elegant tool that gives us a fingerprint of the entire solidification process. It's called thermal analysis, or TA for short. And the concept is actually pretty straightforward. You take a tiny sample of your molten metal, pour it into a special cup that has a thermocouple, and you just record its temperature as it cools down and solidifies. That simple graph of temperature versus time, the cooling curve, is an absolute goldmine of information. It tells you pretty much everything about what's happening in the melt.
To a trained eye, this curve reads like a book. You look for these key events, the liquidus. That's the big one. It's the exact moment the very first crystals start to appear. Then you've got something called undercooling, which shows you how much the liquid had to cool down below its freezing point before solidification really kicked off. And then you see this amazing temperature spike called recalescence, which is caused by a sudden release of energy as the metal solidifies. And finally, the solidus tells you when the whole journey is over. Every one of these points tells a critical part of the story. As the famous metallurgist D.M. Stefanescu basically put it, absolutely every single event during solidification leaves its mark on the shape of this curve. So it's not just a graph, it's a complete diagnostic report on the health and the behavior of your molten metal, before you've even poured the final casting. And this brings us to the ultimate payoff of all this. By understanding the physics and having a tool to measure it in real time, we can shift from being reactive firefighters to being predictive engineers. Quality stops being an accident and starts being a discipline. Because that cooling curve doesn't just tell you what happened in that little sample cup. It lets you predict what will happen in the actual casting. Before you pour a single thing, you can predict the risk of shrinkage, the likelihood you'll form those hard carbides, what the graphite structure will look like, and even the final mechanical properties like hardness and strength. It's incredible. So the new paradigm, the new way of working, looks like this. Step 1. You analyze a sample of your melt with thermal analysis. Step 2. You read that cooling curve to predict the final outcome. Step 3, and this is key, if the prediction is off, say your shrinkage risk is too high, you make proactive adjustments to the melt right then and there. And then step 4, you pour, but now you pour with the confidence that you've already engineered the outcome you want. This just changes the entire equation. Quality control is no longer some passive inspection gate at the end of the line, just there to catch failures after they've already happened and cost you money. Instead, it becomes an active thermodynamic discipline where you're engineering success from the very beginning of the process. And that kind of leaves us with a final thought to chew on. If a process as ancient and as complex as metal casting can be decoded and controlled just by understanding its underlying physics, what other so-called problems in manufacturing, or even in other fields, aren't really problems at all? What if they're just misunderstood physics, waiting for the right tool and the right perspective to finally be solved?